Well, what if you don't have sort of masses which are all at discrete little locations where you can use the sum, or you're looking at objects that somebody's already done for you? In other words, what happens if you need to find the moment of inertia in a situation where you've got to use this integral? So that would be a continuous mass, which just means you've got an object where the mass is kind of smeared out over a whole bunch of different locations. So you're going to have to go look at each little tiny bit of mass and look at that little bits of mass's location. So an example of this would be a uniform disk. And by uniform, we just means uniform density. So that just means the mass is sort of uniformly spread out over the whole object. It's not kind of concentrated in one spot or another. So if we did a uniform disk, so I'm going to try and do, a little bit of three-dimensional things here, like that. So we've got a thickness of the disk. We'll call that T. No, we won't call it T, that's time. Let's call it L. And then we'll have our radius of the disk. And we'll call that big R here. And the disk will have a total mass, and we'll call that M. And so here we've got, a disk. It's got mass, it's uniform, so that mass is kind of spread out all over it. And the total mass, that's sort of this big M. All right, so what's the moment of inertia going to be? Well, the first thing that we can tell, or that we need to do, is figure out what's our axis of rotation. So let's do the one that kind of goes through the center here. So then it goes back like that, out there. So this will be our axis of rotation. So let's draw it sort of face on like this. So if there's our disk, here's our axis of rotation coming out of the middle. So we're like rotating it like that or like that, swirling it around this axis. Okay. How do we find this? Well, the first thing, now that we know that the axis of rotation is here, we can say it's going to be smaller than just the total mass times the total radius squared. Because the only bit of mass that's at that big radius, big R, is this stuff out on the edge. All the rest of the mass is closer in. So that's going to all lead to some mass being at smaller radii than R. And so the moment of inertia will be smaller than just total mass times R squared. So then how do we figure that out? All right, so we need to find a little chunk of mass that's all at the same distance. So let's just do a test distance, little r like that. And all the mass that is at that distance is all the mass that's in a circle around like this. So let's redraw that. We do just that little bit of mass. It would look like this. It'd be very, very thin. It'd have the same thickness as the whole disk, that thickness L. And I guess now that we're doing a little thin thing, we could see it on the other side as well. So that would be our little bit of mass. It would be distance R. So if we want to know the little bit of mass here, well, that is going to be the density times the volume. So that will be our little bit of mass, dm. So what's the density? Well, they didn't give it to us, but we'll just call it rho for now. So that's the density times the volume. That'll be the length times the width times the thickness. And yay, we know the thickness. The thickness is L. The length, well, that's going to be the length around this way. So we could actually say if we just like cut it like there, we'd actually have a strip like this. And it would have thickness L. So the thickness there would be L. The width here, well, we're looking for just a little bit of mass, so I guess the width would just be a little bit of distance along the radius. So this would be dr here. I know I'm getting a little crowded there, but that's the width. What's the length here? Well, that's going to be the circumference of the circle. So here, that's going to be 2 pi little r, and then times density. So this is our dm. Okay, so we'll write this up here. A little bit of mass dm at distance r from the axis of rotation. And that's the really important bit. It has to be the bit of mass that's all at the same distance r from the axis of rotation. That dm is equal to the density, rho, times the length, 2 pi r, times the width, which is our tiny bit of distance, that is the thickness right here, this thickness right there of this little circle, times the thickness of the whole disk itself. Sorry, I should have said this is the width of this little circle here, so like this amount, or like right there. That's what dr is. Okay, so now we've got that. I guess let's go ahead and figure out what the density rho is. So this is the density. And that's going to be mass over volume. So we basically have that here. We could solve this, but that's not really going to be useful for us. We want to solve this for something else we can plug into this equation. But we could also do the total mass, m, over the total volume. And well, what's that going to be? That's going to be the area times the thickness. And so we got our total mass m. The area, well, I guess that'll be pi, the total radius, big R squared. That's the area of the disk, and the thickness is L. So that's our density. So we could actually plug that in here. So dm is the total mass over pi r squared L. That's the volume of our whole disk, the total volume of the disk. So that's the density. Times 2 pi little r squared, because this is the mass just at this tiny little ring, this little red ring here, not the whole disk. So that guy times dr times L, and L will cancel. So it turns out the thickness of the disk doesn't matter. And that makes sense because, you know, even as you move back, you're not changing distance from the axis of rotation. So it doesn't matter like how much we spread the mass out this way. It only matters if we take it farther and farther away from the axis of rotation. So L cancels out, pi cancels out, and we are left with, let's move all the constants in front. That would be a 2, that 2, the mass, and then the total radius, big R. It's a constant because it's the radius of the full disk. It's not changing as we walk out from the middle to that big radius. So those are constants, and we're left with R dr. All right, so there's our dm. So now let's plug it in to our moment of inertia equation. So 2 total mass over the total radius squared times little r times dr. That's my dm, boop, boop, times r squared, which we're just coming down from the definition. All right, then I guess we got to figure out what are our integration limits. What are the different little radii that we're looking at? So we go from the smallest to the biggest, and the smallest the radius ever gets, well, that's right in the middle, so that's 0. And the biggest the radius gets, I guess that would be when we're out here at the outer radius, the full radius. So that's big R. All right, so let's take the constants outside. This 2 times the total mass times r squared. And then we got our integration limits. 0 down here is the smallest, big R up here is the biggest. And we've got r and r squared. So as we integrate over r, we'll be doing it for r cubed. And we can do that integration. It's a nice little power integration. So r to the third, that would become 1 more power of r to the fourth. We would divide by that power, and then we'd have to plug in our integration limits. at little r equals 0, and at little r equals the big total radius. And we would get the moment of inertia, well, I guess the 2 and part of the 4 would cancel, so we'd get 1/2 mass r squared, and then we'd get r to the 4th minus 0 to the 4th, or we'd get our moment of inertia is 1/2, 2 of those r's would cancel, mass r to the 4th. And kind of as we said at the beginning, this is for a disk that we're rotating about the center like this. It should be less than the total mass at the total, oops, did that wrong, at the total radius squared. So just sort of forgot. r4 here divided by r squared there, that should just be r to the 2nd. And it's less than just the total mass times the total radius squared, because a lot of the mass is in closer than that total big R radius squared. And quickly reviewing what we did, we need to find a little bit of mass that was all at the same distance r, and we needed to do that because we're multiplying this little bit of mass times r, and we need that number to be the same for each little chunk of mass. So we went over here to find how much mass is at the same distance little r, so we did in red this sort of test distance r, and that gave us, okay, so it'll be r, the length of this little strip of mass is going to be the radius, 2 pi little r. The width is just going to be this little tiny infinitesimal thickness, dr, because that's what we're walking over here, dr. And then the thickness is going to be just L, the thickness of the whole disk. So that got us the little bit of mass. We found density using the mass and total volume of the whole disk. Plug that in here for density. Got our little dm in terms of variables that we were given here, at least in symbol form, and our integration limit, which is little r, and then we just plugged it into the integral and went through and did our integral and got our answer.